Solarius PV is the ACCA software solution that assists PV system designers and installers to correctly size and assess grid-connected photovoltaic systems. With its user-friendly interface and a unique step-by-step assisted design editor, we'll be able to address the various aspects of system design and see how professional Solarius PV can be, covering each design phase starting from site assessments in terms of solar radiation studies, leading to the preparation of all necessary construction documents and design layouts, together with the single-line electrical diagrams and a detailed financial analysis of the system for a precise feasibility analysis to present to our client. So let's get started. After launching the program, the first thing we see is the program's homepage. This section allows us to create a new file, choosing between a low voltage system, a three-phase system, and medium voltage system. Open, which allows us to open project files previously created and access the program example folder or search among recent files. We can also access the options section, where we can set up some default properties, the backup folder, the measurement unit, and so on. Here we can access the online services, which are completely free. We're talking about the technical support service, our discussion forums. We have the video tutorial section and possible updates for the program, which are completely free for our users. In particular, we'll be focusing on designing a photovoltaic system on the roof of a residential building with the practical approach, where we'll be taking care of analyzing and studying the technical and financial feasibility aspects. When creating a new file, the program immediately opens up a structure here on the left side of the interface, composed of a tree view navigator. This allows us to identify the logical steps to consider in order to draw up the entire project. More specifically, in the general data section, we find the client and designer nodes, where besides having the possibility to manually enter data relating to the client and the designer, we can take the advantage of one of the program's data acquisition features, extracting such information directly from another Solarius file. Typically, we can use this function to also import information relating to generators, subsystems, consumption, or system descriptions. One of the main design aspects of Solarius is to characterize the solar radiation data. This data is obviously necessary to design and size the system, as it will allow us to understand whether the site is valid for a PV system installation or not. So let's go ahead and use the specific Open Location Archive tool. This dialog here allows us to access the Locations Archive, organized according to a wide range of world locations and provided by the Meteornorm 7.1 database, with the relating horizontal plane solar irradiation values for each city. In addition to the program archive, you can also customize your locations using the user archive, where you can define your own location should it not be available in the program. Once the location has been defined, we can follow three main design methods. We can insert the data manually, so let's define a name of any location, and with the mouse here indicate the fields where to insert the data. We can also import data from the PV GIS portal for other European, African or Asiatic locations. This is obviously a free database supplied with the program. And the third method is to import location data using the Google Maps layout in order to retrieve solar irradiation data from the Meteornorm 7.1 database, together with the site's altitude values. When it comes to the shading analysis, the program provides us with a shading factor section where we can type in the shading factor. We can do this either manually or by completing a locations photo survey to generate the relating solar diagram. Automatic calculation is obtained after having defined the locations photographic survey in the program, indicating where the system will be installed. In order to do this, a special function will help us assemble the single photos from a site survey into a single 360 panorama photo. With regard to site survey activities, in order to prepare the inspection correctly, you need to be positioned with your back towards the installation area. And using a camera, we can take a series of photos starting from left to right. Let's say from latitude minus 120 degrees pointing south to plus 120 degrees pointing north in the northern hemisphere, and vice versa for the southern hemisphere. So during the inspection phase, the two reference points assume a great importance in order to identify azimuth and the 2 points on the horizon that represent the tilt angle. Once we have the single panorama camera shots, we can load the photos and assemble the entire panorama photo that obviously covers a 360-degree area. We'll easily compose our pano photo by simply overlaying each photo so that they correspond to the previous photo. At this stage, once we confirm this operation, all we need to do is adapt the solar diagram to our site photo. We can do this by specifying the relevant site info as retrieved during the inspection phase. At this point, we'll activate the horizontal axis calibration tool and insert the height value in degrees as obtained from the site inspection sheet. Here we'll simply select the 0-degree line on the horizon and position it carefully as shown in the figure below. We'll also take into account the two reference points identified using a compass. After having completed this step, we can now view the sun's path for each period of the year and verify the maximum solar irradiation. A very useful feature allowing us to verify the best exposure for our photovoltaic modules. The program's efficiency calculation panel here shows that maximum irradiation is obtained at 0 azimuth. Therefore, with a south exposed system and a 32-degree inclination. As a general rule of practice, modules can be placed according to a south orientation with a tilt inclination equal to the location's altitude minus 10 degrees. But if this rule is valid, why are we using a software? For an optimized module positioning, we also need to take into account the presence of hills, valleys, mountains, trees and any other obstacles, such as buildings on the horizon that may influence the amount of solar radiation that may affect our PV system. In fact, once we have defined these parameters correctly, we can see how the shading factor has changed from 1 to 0.98. This obviously means that the solar irradiation also changes, indicating that we have less solar energy available due to the effects of shading. This assessment allows us to define our system and judge its feasibility, both in terms of its production levels and its cost. Of course, we'll be seeing these aspects in more detail afterwards. This info will allow us to implement the system with the maximum irradiation and acquire the effective loss due to positioning, for example because of the surrounding architectural and landscaping characteristics. The albedo coefficient would allow us to determine the energy surplus due to reflectivity of surrounding surfaces. Dark surfaces will have a low albedo value, whereas lighter surfaces will have a higher value. When proceeding with system design, we can start off from all of the previously defined specifications, including the single-phase system type that we selected earlier. In this section, we'll add a site description, address and postcode, Let's now set the system design working drawing. For this system, we'll add a single generator, even though a system with a multi-MPPT inverters could also be adopted. This is very useful, for example, for PV systems placed on different surfaces but belonging to the same building. In this assisted design section, the technician is also guided by a step-by-step wizard from a CAD file to the final module layout solution. In this first step, we can design our system surface both in plan or in elevation view using special functions including a DXF DWG CAD file import as a reference. With the area plan of our site or building loaded, we can now specify the size of the area where we want to position our PV modules. Here we'll select the new surface in plan view. We'll then activate the snap functions, then proceed to drawing the surface in plan view. Then we can specify the indicated parameters in the section properties. We'll set the 30-degree tilt. Then enable the obstacles function. This is a specific tool which allows us to mark out any obstacles around our installation surface. Here we'll set the obstacles height from ground level and set it to 12 meters. Then of course we'll set the site orientation with the north symbol. We'll set this to 45 degrees. In the solar irradiation section, we can determine whether the system is coplanar to the designed surface or not. In case of non-coplanar systems, we can additionally specify if the mounting structure is mobile or if along any axes. In our specific case, the system that we're going to see is on a roof and coplanar to the surface. For the next step in the module section, we can select the type of module from a components archive featuring more than 24,000 modules. Having previously set the project specifications, we can decide whether to size our system according to maximum energy values or according to a specific power range or energy requirement. In our case, we'll set the system to 4.5 kilowatts as a specific power value and with a manual spacing between modules and vertical positioning. If we press the calculate button here, all compatible modules are retrieved from the archive and listed in the table below. Once all modules are set, we can apply filters by supplier, power rating, and so on. We're going to rearrange this table here, sorting the data according to those among the 250 watt power range. With this info at hand, the software will dynamically calculate the number of modules necessary to meet our project criteria. Moving on, the program will also show all of the inverters from the components archive which are compatible with our PV system as defined so far. In particular, the designer can select the compatible inverter by setting specific conditions to layout. We can even operate on the electrical safety margins or vary the control temperatures. In this last step of the assisted design wizard, you'll get the final installation surface layout with the possibility of inserting other graphical details and objects such as inverters, electrical panels, or other descriptive notes. To conclude the assisted design procedure, we can extract the summary of the designed generator, the module layout, which can also be obviously exported in the CAD format, and a summary of the electrical verifications. The second and probably the most important phase for the PV system documentation is the automatic single-line electrical diagram generation. With the help of this special wizard, you can define all relevant specifications for electrical switch panels, AC and DC cables, and the system protection devices. When we close the wizard, we'll then be able to see a tree view structure of our system from an electrical diagram point of view, which can also be contextualized for each single node with system specifications. We can now view the detailed single line electrical diagram and customize the title block format. So far we've seen how to generate a basic single line electrical diagram, but we'll now see another feature that allows us to obtain a new diagram that we can then obviously customize by using some protection devices such as surge protection devices and diodes, etc. Let's continue and move on to evaluating the system's financial analysis aspects and verify the typical investment specifications. In the cost estimate section, which is integrated with Primus, our bill of quantities and cost estimate solution, we can assess all of the elements imported within the project or simply insert a cost per kilowatt and quantify any recurring or one-off management costs. The program will now generate a table and a graphical summary both in table and graphical forms, which can then be exported with these functions here. On the following node, we can select the consumptions node. From this section, the designer can insert the specific electrical consumptions for each kind of appliance. So let's try adding one manually, for example, a washing machine. We can add the appliance, define its specifications, unit of measurement, the period of use, supposing that in August the family is in holiday and that all the washing activities occur during the odd days and at weekends excluding Sundays. We can now characterize the consumptions and the operating hours. By confirming, we then get the appliance's total consumption over a given period. Alternatively, we can choose minutes as the unit of measure and set the relating value. We may find it easier to specify a percentage measurement basis on the daily energy field together with the profiles settings. Alternatively, we can represent the analysis with the help of the software profile archive, from where we can load a consumption profile of a family of 4 people and obtain the estimated consumption trends. After getting the hourly data, we also obtain the consumption and electrical balance coverage. In particular, the consumption coverage section allows us to distinguish between grid coverage and the system coverage rates. At this point, we just need to view the budget and verify the system feasibility from a financial point of view. Here we can choose between different financing systems. In detail, the program can allow to view the profitability analysis and annual budget both in diagram or graphical forms. Before producing the technical and financial reports, we can also evaluate the value and view the information relating to the avoided emissions in the atmosphere. At this stage, we're now ready to print our technical and financial reports. These are generated automatically on the basis of our input data. and can be obviously printed or exported in the RTF format or in the PDF format, or we can even modify the contents of our reports within the software with this specific edit report function. With regard to the financial report, we can even include the certificate for avoided emissions in the atmosphere if necessary. When we proceed to filling in the form, notice how the software automatically completes the report with all of the information relating to the project as defined so far. But that's not all. The software, as said earlier, guides us throughout the system design. In fact, the integrated diagnostics tools monitors any errors in the project. As previously mentioned, an additional software feature allows us to view how our PV system will be positioned on our building. By accessing our View on Photo function, we can simulate the visual impact of our designed PV system directly on a real photo of our building. Let's load our reference photo, then continue to inserting the installation surface. Then we'll identify our vanishing lines and determine the correct measurements. The first reference vanishing line measurement is 4 meters 50 centimeters, which represents a true measurement acquired on site. This will be our reference measurement. Next, we'll insert the second vanishing line and set it as 6 meters as its reference measurement. Confirming this phase, we can then move on to defining the installation surface with the designed PV system. Once the surface has been selected, we can carefully overlay it on our 3D representation or photo in order to obtain the photorealistic view of our PV system. Let's now enable the project view and see the result of our photo simulation. As we have seen with Solarius PV, you can design a photovoltaic project from the moment you locate the installation site with relating irradiation data, while you set your technical project and single line diagram to the financial report and all other necessary project documents. All design aspects of your solar PV system are covered by a single software at a very convenient price.